नमस्कार, सुस्वागतम, अभिनंदन, केम छो, आदाबर्स, खुशामदीद एंड वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का 83वें PRL के अमृत व्याख्यान में स्वागत करता हूं, अभिनंदन करता हूं। I, Anil Bharadwaj, very warmly welcome all of you for the 83rd PRL का अमृत व्याख्यान। This is also the 8th monthly Vyakhyan of PRL का अमृत व्याख्यान 2.0. We started the 75 episode series of Vyakhyan on 4th of August 2021 and completed this 75 episode happening every Wednesday at 4 p.m. which was completed on 5th of January 2023, that is this year. PRL, as we all know, was established in the year 1947, that is the year of our independence, and it was established by none other than Dr. Vikram Sarabhai, the father of Indian space program. So as we celebrate Azadi Ka Amrit Mahotsav, we also celebrate PRL's Platinum Jubilee, and PRL Ka Amrit Vyakhyan is one of the way we are celebrating the Platinum Jubilee of PRL. Today, that is 9th of August 2023, that is Wednesday at 4 p.m. We have a very distinguished Vyakhyankarta with us, Professor Subir Sarkar, who is at Department of Physics at University of Oxford in United Kingdom. And he's going to speak on seeing the high energy universe with IceCubes. We greatly appreciate and thank Professor Sarkar for accepting our invitation and remotely joining us on PRL's Ka Amrit Vyakhyan. This is the Vyakhyan which will be delivered by him sitting within the country in Kolkata, but remotely because he is unable to join us in person. But we are really fortunate that he has agreed to join us on this 83rd Vyakhyan. I would now request my colleague, Professor Shubhavati Goswami, to kindly introduce our today's Vyakhyankarta to the audience at the WebEx panel, as well as those who have joined us live on the PRL's YouTube channel. Over to you, Professor Goswami.
Thank you, Professor Bharadwaj. It's a real privilege for me to introduce Professor Subir Sarkar. In fact, this is the second time this year that I am getting this opportunity to introduce him. Earlier, it was for the INSA Royal Society meeting. So, Professor Sarkar received his PhD in 1982 from TIFR, and he was a staff member there from up to 1984 in the cosmic ray group. Since 1990, he has been at the University of Oxford, where he was appointed professor in 2006 and head of the particle theory group during 2011 to 2019. He has broad interests at the interface of fundamental physics with astrophysics and cosmology, dark matter, dark energy, inflation, and the cosmic microwave background, primordial nucleosynthesis, etc. He also works on high energy cosmic rays, gamma rays, and neutrinos, and belongs to the IceCube Neutrino Observatory since 2004, and also the Cherenkov Telescope Array from 2010. Earlier, he worked on the Pierre Roger Observatory from 2003 to 12 and the CERN BEVC Beam Dome Experiment 1985. In 2017, he was awarded the IUPAC TIFR Homi Bhabha Prize for distinguished contributions in the field of high energy cosmic ray physics and astroparticle physics over an extended academic career. And in 2021, he shared in the Bruno Rossi Prize of the American Astronomical Society to the IceCube collaboration for the discovery of a high energy neutrino flux of astrophysical origin. I would personally like to thank Professor Sarkar for accepting our invitation at a very short notice. And this is, IceCube experiment has been giving us fantastic results. And only recently we had some nice results from IceCube. So we thought it's a very good time to have this Vyakhyan. And so over to you, Shubirda, for your vacuum.
Thank you very much, Shubha, and thank you, Professor Bharadwaj, for inviting me to speak in this series. Can you see my screen, or do I need to share it?
So it's not
You have to
seen.
share
You have to
it.
share it.
I have to share it. Okay.
Yeah.
Is it all right
Yeah, it's
now?
coming. It's coming
It's
up.
coming.
Yes,
It's coming.
perfect.
Yeah.
Excellent. So I would like to talk about, as Shubha said, work that I'm engaged in currently as a member of the IceCube experiment, which is at the South Pole, an extraordinary experiment that is a telescope buried a kilometer deep in the Antarctic ice cap. But the processes we are studying are just those that neutrino physicists study in the laboratory, namely deep inelastic scattering, or rather the scattering of a neutrino of a nucleus, which results in a visible signal that can be detected in our experiment and by others. And with this, what we are trying to do is to open essentially a new window onto the universe, in particular the most energetic phenomena out there, such as the gigantic black holes that lurk at the centers of galaxies, so-called active galactic nuclei, quasars, and gamma ray bursts, mini quasars, pulsars, and so on. And this talk is going to therefore range, as I was instructed, since it's meant for a broad audience, it's going to range over a wide set of topics. And I'll try and bring out some of the synergies between this way of looking at the universe and others that you have heard about, including quite recently from Tarun Saurabh about gravitational waves. But before I start, I would just like to say that this talk, since it's on cosmic ray physics, I would like to dedicate to the memory of Bibha Chaudhary, who in the 1970s, as you know, worked in your laboratory on cosmic rays, and before that at TIFR. She was an extraordinary woman, a pioneer in the field, and I don't think we yet know the full story of her academic research and investigations and exactly how she did what she did. But nevertheless, she is certainly someone that I hope will be a role model for others like her to join our field. So let me start at the very beginning. We know that astronomy is about detecting photons from the universe and trying to make sense of them. As our ability to detect photons of different frequencies or energies, shown here on the top axis, has increased, we have gone from studying just optical photons, which is this map in black here, to, for example, seeing the universe in radio waves. This happened around the time of the Second World War. And subsequently, experiments were flown on first on rockets and then on satellites to look at the X-ray universe. This cannot be done from the ground because of absorption by the atmosphere. And then finally, gamma rays. And today there are telescopes looking both from space and from the ground at higher energies at the high energy gamma ray universe. But there is a limit to what we can do with photons, because above some energy, which is of order 10 TeV, so a TeV is 1,000 GeV. GeV is the mass of a proton. And just for context, the energy in the Large Hadron Collider is about 10 TeV. So above this energy, photons cannot come to us from the distant universe, because on their way, they will hit a photon of the cosmic infrared background. And although photons normally do not scatter on each other, when the energy is high enough, they can, because they can create a pair of electrons, positrons in the center of mass, and that will attenuate them. If you want to go higher in energy to look at the universe, we have to then use particles. And the original particles are cosmic rays, which are mainly protons with heavy nuclei, electrons, etc. Now, those allow us to look indeed to much, much higher energies, but eventually they too will interact with the photons that pervade all through space, in particular the cosmic microwave background. And that happens at an energy of about 10 to the 11 GeV. Because if you think about it, at 10 to the 11 GeV, the mass of a proton is a GeV, so its Lorentz gamma factor is 10 to the 11. And to the proton, the background photon, which is only got an energy of a milli-electron volt, is boosted to about 100 MeV. So it can then excite the proton to a delta plus resonance, and that stops it from propagating further. However, if we use neutrinos, which is this green line that is marked here, then you can essentially look at all energies. The universe is transparent right back to very early epochs in the Big Bang, up to a redshift of 10 to the 12, when ultimately neutrinos also thermalize, but we can essentially see the entire universe. Now, the experimental techniques that are used to study this kind of high energy particles are quite varied. So let me just give you a broad sketch. So essentially, we are looking at very low fluxes of particles. So you need to instrument very large areas or volumes. And the cheapest way to do that is to cover a large bit of earth, land, with scintillators or so-called water Cherenkov detectors. These are essentially detectors that detect radiation from ionizing particles. So these ionizing particles are created when a cosmic ray hits a nucleus in the Earth's atmosphere, which is in fact protecting us from these cosmic rays. And that interaction creates a so-called air shower where the secondary particles create more secondaries and so on. The theory of this incidentally was given by Homi Bhabha and Heitler long ago, about 100 years ago, nearly. And these secondary particles then reach the ground and trigger our detectors. They also create, indeed, the only particles that survive long enough to reach the ground are muons, which in the rest frame have a lifetime of only a couple of microseconds. But again, because of the Lorentz boost at these high energies, they live long enough to reach the ground. And we can try and detect these. In addition to that, we can build the instrumented detectors underground in large volumes of water or ice. The reason being, in the ice or water, the muons are traveling faster than the speed of light in the medium. And therefore, they send out like a shock wave, a light shock wave. We call it Cherenkov radiation. And that is the telltale signature of ionizing particles. You also emit photons from the air shower, which are more or less aligned with the incoming particle. So if you have a large telescope which can look along the shower, you detect it. And these air Cherenkov telescopes have been very successful in terms of bangs per buck, as it were. In fact, there is one not far from you at Mount Abu. The tactic telescope, which is operated by BRC, has been taking data on gamma ray sources. In addition to this, the air shower ionization also excites molecules of nitrogen in the atmosphere, which then emit fluorescence radiation. And this can be detected if you have a very dark night. If you have Schmidt telescopes, which can look over a large angle, they can detect this. It's very faint. So this air shower is like a 40-watt bulb whizzing across the sky, tens of kilometers away, and you have to catch it. Now, all these detectors, as I said, need to be spread over large areas of volumes, and that gets increasingly expensive. So people are now trying to determine if, in addition to looking at these muons and neutrinos, which is the subject of this talk, which in fact are coming from all directions, indeed through the Earth, because the Earth doesn't stop them, whether we can also detect from these showers the radiation that they emit in radio waves. This happens because of charge separation in the air shower. And these radio waves, if we can detect them, would enable us to really build rather cheaply arrays which can cover not just hundreds of thousands, but tens of thousands of square kilometers. So I hope you have got an idea of the broad range of techniques that can be brought to bear on this problem. And with these kind of methods, we have been able to measure the spectrum of cosmic rays over a huge range of energy, starting from about 1 GeV, which is the left-hand end of this plot, all the way to 10 to the 11 GeV, which I mentioned earlier. And as you can see, these energies far exceed anything that we can achieve at the best accelerators on Earth. Now, the cosmic rays are not just protons, they also have heavy nuclei and also a small amount of electrons and indeed antimatter, positrons and antiprotons, which are created through the collisions of these cosmic rays with interstellar matter as they rattle around the galaxy. But because they're deflected by magnetic fields, they don't point back to their sources. And so we still don't know where they come from. We have identified the remnants of supernovae, stellar explosions in the galaxy, as responsible for some of the lower energy cosmic rays around here. And now IceCube has identified two active galactic nuclei. These are the supermassive black holes at the centers of galaxies as the sources of ultra high energy cosmic rays, which then make neutrinos. But you can see there are still a lot of question marks as to what are the other sources where they can be accelerated. The point is that neutrinos are always going to be produced when cosmic rays are created, however they are created. And these neutrinos are produced by interactions with both matter and with photons. So, for example, a proton interacting with the nucleus, just as it does in our Earth's atmosphere, it will do that in a black hole ergosphere or in a gamma ray burst, and it will create a load of particles, mainly pions and kaons, at the end of the cascade, which then decay to give you long-lived particles like muons and, of course, neutrinos. So I have circled the bit that we are after, and you can see that we also expect a particular ratio of neutrino types. This chain, for example, will give us 2 muon neutrinos for every electron neutrino and no tau neutrinos. However, neutrinos, as you know well from your colleagues at PRL, they oscillate between flavors. But the fact is that in this case, we are looking at the oscillations over astronomical baselines. So they essentially equilibrate. All flavors start getting populated. And by the time they reach Earth, there are equal amounts of all flavors. Now, coming back to this cosmic ray spectrum, you can see that there is a change in the slope at this point, and we think this is where the extragalactic particles are coming in. What IceCube has now done is to detect the expected neutrinos, both from the interactions of these cosmic rays in the atmosphere, which is marked here as atmospheric neutrino flux, this steeply falling line. We have also very recently, as Shruva mentioned, detected the galactic neutrino flux from the Milky Way. And of course, we have detected the extraterrestrial neutrino flux from the interactions from the sources of these cosmic rays wherever they are, which is this horizontal line here. It is horizontal because you will notice that the flux has been multiplied by E square in order not to let this curve drop too steeply. So this flat line is actually a e to the minus 2 spectrum. We are still not detected the cosmic ray neutrinos that we expect at the highest energies, which is from interactions of the cosmic rays with microwave radiation. That is this blue line here with a large uncertainty. Those are called cosmogenic neutrinos, and detecting them will be important because that will allow us to probe fundamental interactions at energies up to 100 times larger than we can ever do in any laboratory on Earth. So to catch this kind of cosmic ray monsters, you have to go to very remote places, which are also rather beautiful. This is in Argentina, in the shadow of the Andes Mountains. And what we are sitting on here is a tank filled with water. This is one of about 1,500 tanks, which are part of the Pierre Auger Observatory. So the Pierre Auger Observatory consists of 1,600 detectors like that, which each dot is a tank like that, and it's spread over 3,000 square kilometers in this pampa, as they call it. And each tank is filled with water looked at by photomultiplier tubes, so we can detect the radiation from the air shower when it goes through, and that is then broadcast back to base. In fact, around this site, there are 4 little hills on which you have Schmidt telescopes. Now, these shutters don't open except when it is absolutely pitch black, which is during moonless nights. About 10% of the time, we can dare to open these shutters because they're very sensitive telescopes, but they can track that cosmic ray shower through the atmosphere. And the whole business is monitored and run from the headquarters, which is in a nearby small town called Malargüe. And when the shower comes in, by the time the air shower hits the ground, there can be as many as 10 to the 11 particles in the shower. as many stars as there are in the galaxy. So you can see that we need a big detector to do this, and we have to figure out how to build these detectors as cheaply as possible because you need so many of them. Now, if you happen to be on shift a particular night, as I was, you get to see one of the highest energy particles in the universe. This had an energy of 10 to the 10 GeV. So that's 1,000,000 times higher than the energy in the Large Hadron Collider. And we know the direction of this very well because all the 4 fluorescence detectors caught it and can then track it back. And this patch on the ground is the size of the signal in those tanks which it hit. Now, you might ask, what is so extraordinary about that energy? Well, if I tell you that if you wanted to build a terrestrial accelerator to get up to that energy, you need to make it the size of Mercury's orbit with the kind of technology we have on Earth, which is about 8 or 9 Tesla magnets and all the cryogenics and so on that we have at CERN. So nature is clearly doing something that we can't do on Earth, and we would like to know how. A simple way of trying to figure out what kind of objects can be doing this is to ask uh, how strong a magnetic field or size of object do you need in order to confine such a particle. So the reason why this ring has to be as big as the orbit of Mercury is because with the 9 Tesla magnet, you can't curve a 10 to the 11 GeV proton better than that. So you see here that the objects that are marked out by this simple criterion named after Michael Hillas, who thought of this, are objects which are the most violent explosions in the universe, like gamma ray bursts, which release in a few seconds to a few minutes the entire mass energy of a star, or the active galactic nuclei that I mentioned several times, or the extended lobes of radio galaxies, which are in fact powered by jets of plasma being beamed out from these very central black holes in the active galactic nuclei. We can rule out all the other usual suspects for cosmic accelerators, which fail by orders of magnitude to reach such energy. The LHC is here, as you can see. So it's an interesting question how we can get those energies, but given that nature has given those to us for free, we can, of course, build these detectors, as I said, to try to detect these particles, thereby gaining access to center of mass energies. Now, this is the important criterion because this would make for a fair comparison with the colliders that we build on Earth. And you see, even on those grounds, we can go up to about 1 or 2 orders of magnitude higher than we can do in the laboratory. The price you pay for that is that these experiments at LHC and Tevatron, etc., have controlled beams and very high fluxes, whereas the luminosity of these cosmic rays is very, very low. At this angle, we are getting maybe 1 particle per square kilometer per century. So now you see why you have to build a 3,000 square kilometer array to get a reasonable number of them to do physics with. Now, the flux does not extend beyond this point because this is, as I said, where you expect this so-called Greisen-Zatsepin-Kuzmin cutoff due to the interaction of these protons with the cosmic microwave background, which would attenuate them. And indeed, we see the attenuation. So most of us do think this is the predicted GZK cutoff. However, it could also be that this is just the energy that the cosmic accelerators can reach and they can't go any higher. So there are still questions to be answered here. Now, since our focus is on neutrinos, let me just point out that however those cosmic rays are being accelerated, wherever they're being accelerated, they would be creating neutrinos. And the flux of these neutrinos can be quite simply estimated just from a simple calorimetric argument. So those protons which are being accelerated are interacting with the matter, which could be the accretion disk around the black hole, it could be the circumstellar matter around an exploding star, whatever it is, or with the radiation fields. And when you work out the efficiency with which protons can create neutrinos, you can make a prediction for what kind of a flux you'd expect. Of course, there are many caveats to this. It depends on the composition of the cosmic rays. It depends on exactly how their slope, the spectrum changes, and so on. But we have some order of magnitude estimate of the expected neutrino flux. So now we can do a estimate of what would it take to detect them. But first, let us look at what kind of a target we are going to look at. So as I said, active galactic nuclei are a prime target. And there has been a lot of ideas about how they might accelerate cosmic rays to high energies and create high energy particles as well as gamma rays, which then cascade in the radiation fields, which are in the vicinity of this central black hole at the center of a galaxy. We also have such a black hole in our galaxy, but fortunately for us, that is not feeding. Many galaxies, they're called active because they are in fact accreting matter from a surrounding disk and shooting out these jets of plasma. And we have seen TeV gamma rays from these active galactic nuclei, but we have no direct evidence that we are seeing protons in such objects. Now, you can, of course, look at AGN on the sky and ask if cosmic rays are coming from those directions. And there are some associations, but these may be accidental because magnetic deflections can be several degrees even at these huge energies. So that is why we really need neutrinos, because neutrinos, unlike cosmic rays, travel in straight lines. So do gamma photons, but gammas are absorbed, whereas neutrinos are not absorbed. So they are really the ultimate messenger. They are the best way to do astronomy. The price, of course, you pay for the fact that they're not absorbed on their route to us is that they're also extremely hard to detect, as all neutrino physicists know. So here is your classic back of the envelope calculation of how big a detector you would need to detect neutrinos. Here we are estimating of a PeV energy of 1000 TeV. And we know the cross section, and we know if you take a target with, say, 1 gram per cubic centimeter, say water, then you would expect about one event in a kilometer cube per year. Okay? So it is clear that we have to build a big detector if you want to see these particles. Now, other active galactic nuclei near us have been studied in some depth. Here is Centaurus A, a fascinating object. If you look at it in the optical, you can see that all you see is a big globe of dust, which is glowing with the radiation that the black hole at the center is pumping out, but you can't see anything of the black hole. If you look in the infrared, you can actually see much more. You can even see a spiral galaxy falling in, which will be absorbed by the black hole shortly. If you look, however, in radio, you see the jets of plasma that are being shot out at right angles to the disk. And this is emitting synchrotron radiation. And at the other end of the spectrum, in X-rays, you can also see the jets in synchrotron radiation, but at X-ray wavelengths. These are extremely energetic particles. Question is, what would it look like if I could look at it in neutrinos? Can I peer down and see that actual black hole at the center doing all the dynamics that powers the system? Again, when you make an estimate of the expected flux, it is pretty pitiful. It's no more than of order one event per square kilometer per year. So you see, we need a big detector. You will now understand why we have to build big detectors. And indeed, people are building such detectors all over the world. This is a panorama of experiments. Some of them have been retired already. Some of them were first attempts like Dumont, which was off the coast of Hawaii. Then came Nestor, which is off the coast of Greece, the Peloponnese, place called Pylos. And then there is a working detector, Antares, which is off the coast of France, near Toulon. And this is now being upgraded to be part of a much bigger detector called KM3net, which is a large experiment with two sites, one near Sicily. Meanwhile, there are small neutrino detectors in the Baksan Valley in Japan. As you know about Super Kamiokande, soon to become Hyper Kamiokande. In Siberia, in Lake Baikal, there is a neutrino detector being installed called GVD. And finally, there is IceCube at the South Pole, which I'll talk about more. But there are other experiments under construction. For example, Pacific One in the off the coast of Canada, and Trident, which is in the South China Sea. And meanwhile, people are trying to do radio detection, as I mentioned. So that's both in the Antarctica, Ariana and Ara, and in Greenland, which is this RNOG experiment, which is currently being installed. And the next generation IceCube experiment will employ radio detectors too. You can also fly radio detectors on balloons and thereby observe the entire ice shelf. And such an experiment is ANITA. And the future, there will be something called PUEO. And finally, you can try to detect the air showers directly. And those are experiments called GRAND and Trinity, which are in Utah. So here are just a few quick shots of these experiments just to show how remote and beautiful the locations are. So there are people on Lake Baikal in the winter, they can go out onto the lake and drill holes in the ice and lower their equipment. Pacific One is being installed off the coast of Canada by a professional company that lays undersea cables. Uh, the South China Sea, as I said, will have this Trident experiment with these are all detectors, in fact, laid according to a Penrose tiling. And finally, there is and finally, there is, what's going on? Oh, I'm trying to press the wrong button there. And finally, there is Trinet I mentioned, which is in the Mediterranean at two sites. ARCA is the one that is focused on doing neutrino oscillations, detecting cosmic neutrinos. This is off the coast of Sicily, while ORCA is the smaller detector of the coast of France that will study neutrino oscillations. So let me now move on to IceCube. As I mentioned, this is in Antarctica on the plateau, which is actually at 3,000 meters. It's quite high. And these planes that you see landing there, that comes from McMurdo, which is on the Antarctic coast. And that's the runaway in between. The South Pole Station is actually a huge place that was named after part of the Amundsen, other explorers who first trekked there, Amundsen Scott. And the geographic South Pole is actually right there. And IceCube is in fact across the runaway here. So the building that you might have sometimes seen in publicity shots is basically the building that houses all the computers, and all the equipment is lying on the ice around it. People essentially all live in the South Pole Station. So IceCube was conceived long ago, 1988, in fact, by theorists, Francis Halzen and others. And initially, they built a small detector called AMANDA, Antarctic Muon and Neutrino Detector Array, which was a proof of principle, showed that you could detect neutrinos using such a technique. But it was also realized that in order to detect cosmic neutrinos, you needed a much bigger detector. So the construction of IceCube was started in 2004 and completed in 2011. And just 2 years later, we are very fortunate. We detected an extraterrestrial flux of neutrinos and also measured neutrino oscillations as well as any terrestrial detector. We saw our first source in 2018, made headlines, and an interesting event called a glacial resonance in 2021. And we saw our second source, which is also an active galaxy, a Seyfert galaxy, in 2022. And just this year, we saw our Milky Way neutrinos. So it has been a pretty successful experiment. Now, just to give you an idea of the conditions under which people work at the South Pole, it's of course a very bleak place, but also strangely beautiful when the southern lights, the aurorae, come out in the sky. You know you're at the South Pole because if you look at the compass, all the directions are marked north. And it is now, right now, it is maybe summer here, but it is winter at the South Pole, and the temperature is a balmy -75, going to -95 with the wind chill. But of course, people only go to work in the Antarctic, the austral summer, which is December and January. And what they have done is sunk 86 holes in the ice going down 2.5 kilometers deep, into which they have put down strings carrying detectors such as this. So each of these detectors is about the size of a large ball, and it contains a photomultiplier tube and the associated electronics to digitize the signal and send it up to the surface. It also carries the power, the cable. And there are 5,000 odd modules of these. And incidentally, 99.2% of them are still working after being embedded in the ice. And the uptime of the detector is over 99%. It works 24/7. The total instrumented volume is a kilometer cube as advertised, and that's a gigaton of ice. Now, you might wonder what else we have there. We have a surface array, which is basically just like the Auger experiment. In fact, the tanks are very similar, covering a kilometer square. And deep down here, there is the deep core closely instrumented volume, which has got more closely spaced strings so that we can go down to lower energies in detecting neutrinos, go down to 10 GeV or so. And the cost of this whole thing was quite a lot, $280 million. But if you divide it by 1 gigaton, it works out to only 20 rupees a ton. So that doesn't sound so expensive. Now, this is the equipment with which you drill those holes in the ice. This is the actual hot water drill. Like I said, this building just houses the computers, and all these digital optical modules are prepared and tested elsewhere and then looped together onto that cable. And that cable is lowered into that hole when the hole is dug, because it takes another 2-3 days to freeze up again. And here is an animation showing you how we first dig down through the so-called fern, the top layer, to create a free passage for the hot water drill, which takes 5 megawatts of power and goes down, right down all the way to the bottom. Below that, there is the rock, the original rock, which is at about 2.8 kilometers. And having dug that hole, the drill retreats, and these engineers standing by rapidly lower the string carrying the detectors, which are then frozen into the ice. And after that, you can operate the detector remotely from a laptop. In fact, we do our shifts from anywhere in the world. We don't really need to go to the South Pole. And this is the collaboration, as you see, mainly dominated by North America, but also from Australia and New Zealand and countries in Europe, and also Japan, South Korea, and Taiwan. India will join the Gen 2 upgrade experiment, but currently we have 58 institutions in 14 countries. UK, Oxford, in fact, joined in 2004 when IceCube was proposed. The detection principle, as I mentioned, is to look for the Cherenkov light, which is emitted by a particle moving faster than light in the ice. And such a muon is created by a so-called charge current reaction by exchanging a W boson. And you can detect that from this three-dimensional array of sensors that I showed you are deployed in the ice. And since you know the time, the amplitude, and the position, you can reconstruct what direction they came from. And because the muon is nearly in the same direction as the neutrino, there is no transverse momentum, we can do astronomy with this. So here is an animation of a very high energy neutrino creating a muon that then comes in and travels to the detector, creating the Cherenkov shock wave. And you can see how the detectors light up. The height of these is proportional to the amplitude, and the color tells us the timing, which is good to better than a nanosecond, so you can reconstruct the track rather well. However, if you have an electron neutrino or a tau neutrino coming in, then the final state leptons they produce can't travel as far as a muon, so they create sort of blobs of light, which we call cascades. In fact, a tau neutrino can create a tau lepton, which then travels for a few hundred meters and then decays. So that's a so-called double bang event. And these we call tracks. Now, a track, as you can see, has very good pointing, but not so good energy measurement because part of it escapes our detector. Whereas with these, we measure the energy rather well, but the pointing is not very good, although it has improved a lot because we are now using sophisticated machine learning methods to try to recreate the direction. And as I said, in 2013, in fact, in 2011, we saw these events. We published it after some time. These were actually discovered serendipitously. These are the first extraterrestrial neutrino events we detected, which the students named after characters from Sesame Street, Bert and Ernie. And you can see the scale of these events. This one is as big as the Eiffel Tower. That's how large a signature is of an event that energetic. And in fact, this was crowned the breakthrough of the year. We are all very pleased that the detector had, in fact, worked. You can't always tell in experimental physics if your gamble is going to pay off. This one did. The challenge is formidable because this is for the neutrino experts in the audience. I just thought I would show you that it's not easy to get those two events because you are after a signal which is shown here in orange, and the background of neutrinos and muons from the atmosphere is many, many orders of magnitude larger. So this is a logarithmic range. So the muon flux goes up to 1 billion times larger. What we noticed was that whereas the muons are created in the air showers, the neutrinos, in fact, are also created in the same air showers, and their flux is a lot lower, but still a lot higher than what we are after. But we realized that we can cut out these neutrinos from the atmosphere by simply requiring that the event that we are after occur within the detector. So we use the outer part of the detector as a veto. We insist that the event should not happen, the conversion of the neutrino to the muon should not happen outside the detector. It can only happen inside the detector. Okay. So pictorially, what you're saying is that if an event happens within this veto, we reject it if it triggers that veto part. So we therefore drop all that background and we isolate only the events which are triggered by extraterrestrial neutrinos. And that spectrum, as you see from this data shown here, is harder, in fact, has a flatter slope, that is e to the -2 slope, than the atmospheric background, which is falling away more steeply. And we established that this was present at sufficiently high significance that we could claim the detection of extraterrestrial neutrinos. But just to give a perspective on this, we see about 10 of these events per year. By comparison, we see 100,000 neutrinos from the atmosphere, and we see 100 million muons from the atmosphere. Okay. Now, these, of course, are also interesting for physics, especially for neutrino oscillation studies. But the astrophysical flux is very, very small, and it takes a lot of ingenuity to isolate it from these so-called backgrounds. Now, let me quickly come to multi-messenger astronomy, because that is something that a lot of people are interested in these days. So as you know, traditionally, we have relied on photons to do astronomy. And occasionally, we discover things there which are of fundamental physics interest, like the cosmic microwave background, or indeed objects like pulsars. These were rewarded by Nobel Prizes. Cosmic rays, too, got a Nobel Prize for the discovery now over 100 years ago. And more recently, as I said, we have started detecting extraterrestrial neutrinos, which are very much the focus of experiments on Earth, and have also been detected from the Sun and from supernova 1987A, but only at MeV energies. We are talking about much, much higher energies. Now, we have also detected the first sources of these neutrinos, and now we have a new window on the sky in gravitational waves. So the game is on to try and see whether by combining these different windows on the universe, we can learn something about the objects that create one or more of the signals simultaneously, and thereby understand the physics of the engines that drive them. To do this, we have set up an alert system in IceCube. Every time we see a high-energy neutrino, it automatically fires off a telegram to all observatories around the world. For example, optical telescopes, say X-ray satellite, the LIGO gravitational wave detector. Anybody who is actually looking all the time at the sky gets an alert. And we rank the alerts as to how significant we think the event is, that is to say, how likely it is to be a cosmic neutrino rather than an atmospheric neutrino. Now, these alerts paid off because in 2017, we issued a neutrino alert that a 290 TeV neon neutrino had crossed our detector almost horizontally, and it came from some particular direction in the sky with a large error box. But because we sent out the alert, we soon heard that Fermi, which is a gamma ray satellite in orbit, had seen a flare of gamma rays from a source in our error box, which it could identify more precisely. And then on the ground, the magic gamma ray telescope saw gamma rays up to 400 GeV subsequently. And there was a long campaign of follow-up observations from radio through to gamma rays, which identified this particular object, which is a so-called blazar, which is one of these active galactic nuclei where the beam is pointing straight at us, so it looks particularly bright. It's like looking down the barrel of the gun. And the redshift of the host galaxy was also measured. This is pretty far away, okay? And it was therefore definitely an extragalactic object that had fired this neutrino at us. In fact, we looked in our archival data and we discovered that this object had fired neutrinos at us previously, but it had not flared, so we had not been able to detect it above the background. But now that we know where it is, we can accumulate all that data and establish that it has been periodically emitting high energy neutrinos. The question then arises, why do we only see this one blazar 4 billion light years away? What about the closer ones? Is it just because they're not pointing at us, or is there something else? So these are questions that you can only answer when you have more data and other multi-messenger probes to provide complementary information. So let me speed up a little bit because I see a few more topics to cover. So this is a gamma ray burst, in fact, the brightest one of all time, which was detected just last year, but we didn't see any neutrinos from it. In fact, we have been looking at neutrinos from other gamma ray bursts and never found any. And that is rather a surprise because there had been tons of theoretical papers saying we should see cosmic rays and neutrinos from gamma ray bursts. But, as Feynman famously said, there is nothing like observations to tell us how nature really works and to keep theorists in line, because one experiment is worth many speculations in that regard. However, theory has worked okay when it comes to our own galaxy, because we know that our galaxy hosts sources of cosmic rays, primarily supernova remnants, which have the required energy. And these cosmic rays diffuse in the galaxy and light it up in gamma rays, which we do see with satellites like Fermi-LAT. And we can then expect that we should see neutrinos from the pi naught mesons that are created by the cosmic ray interactions. And we therefore look for these neutrinos, and using sophisticated so-called convolutional neural networks, which sift through years of data and on the template of the gamma rays, and they manage to identify a signal in neutrinos, not quite at 5 sigma, but close enough that it's rather interesting. And we can now say that we can detect the neutrinos that we had always expected from the galaxy. This is still the most fuzzy preliminary image of the Milky Way, which, after all, let's face it, we only learned was a galaxy about 100 years ago. So 100 years later, we have now seen it in neutrinos. But this other window that has opened on the sky, meanwhile, in gravitational waves, you have heard about. I'll remind you that it started with this measurement of this black hole merger, which created tiny ripples in space-time that were picked up by the LIGO detectors. And that chirrup signal, which was also a theoretically expected calculation of how two black holes, when merging, how they distort space-time so as to create that signal, that was seen by these detectors. Now, with two detectors, you can't identify the source on the sky. You can only identify a great circle. But every other telescope in the world also looked to see if they could see anything from that great circle. And so far, we have seen nothing, although that is not unexpected for black holes. However, when there was a neutron star merger, there was an expectation that we should see other things like photons and perhaps even neutrinos. Now, photons were indeed seen. Here is the Swift and the Fermi-LAT and the gamma ray burst monitor error box, which identified where that particular neutron star merger is. But I have to say that we didn't see anything in neutrinos either in Antares or COMLAND or IceCube. We did see some neutrinos at the same time, but they were quite away from the location of that neutron star merger. Now, just a little aside to say, all this time I've been talking about high energy neutrinos, but we see some event rate. How do you interpret that in terms of a flux? To do that, you have to know the cross section. But these are the neutrinos and energies which are orders of magnitude higher than any you have created in the laboratory. So how do you know at what rate do they interact? I mentioned that they interact through deep inelastic scattering, which is this process here, through the exchange of a W boson. The neutrino converts to a charged lepton and creates a cascade as well as the outgoing lepton. And this process basically, most of the contribution to this cross section, as you might expect, comes when the transverse momentum that is transferred in this process is of order the mass of the propagator square, and x is the fraction of the proton momentum that is carried by the parton that is struck in the proton, and that is given by this formula here. So you can see as the neutrino energy increases, this x, which is called the Bjorken x, decreases. So at higher energies, we are looking into the proton at smaller and smaller momenta, and the distribution of partons in the proton is called the parton distribution function, as it says here. And these can be measured at accelerators. For example, at the Hera accelerator in Hamburg, they scattered electrons on protons. So barring the electric charge on the electron, it's just like a neutrino. It also interacts weakly. So we can measure those PDFs. And if we want to know what the value of this PDFs is at higher energies, we can propagate them in the theory of perturbative quantum chromodynamics using the so-called Dogitzer, Gribov, Lipatov-Baltarelli-Parisi equations, and that gives us a prediction for the neutrino cross-section at high energies. Now, this calculation we did using the measurements of the PDFs that were done at Hera. So you may have heard that the proton is made out of 2 up quarks and a down quark. That's here, okay? But you see, as we go to lower values of x, most of the proton actually is made out of virtual gluons, which is this band here, and of course virtual quarks. But the gluons are dominant. In fact, they have been multiplied here by a factor of 1/20 to bring them down to the point where you can compare them here. So essentially the proton is just a ball of gluons at very low x. And the PDFs, as they're called, change with the momentum transfer square according to a formula that you can calculate from perturbative QCD. And the agreement of theory and data is excellent. So you know that this is a valid theory. So this also allows us to predict the neutrino cross section up to about 10 to the 8 GeV with few percent accuracy. And in addition, there are other processes which neutrinos undergo. So for example, this was one that was predicted in 1959 by Shelley Glashow, that a neutrino can interact with an electron and create a W boson on shell. In other words, a real W boson, which then decays in the ice. And that signature is very characteristic, and we are able to isolate it from all the other kinds of events. And this happens at a characteristic energy of 6.3 peta-electron volts, and we measured the energy to be just that. So this was kind of fun. This is the expected process in the standard model, but nobody had ever been able to create it on shell W in a deep inelastic scattering interaction. This cross section I mentioned allows us to do a cross check using the fact that although neutrinos, as I said, travel through the universe, at high energies the cross section does increase as we calculated. As you see here, it goes as energy to the 0.3 roughly, and then there is the Glashow resonance superimposed on top. So you can see that the energy cross section is rising to the point where actually at something like 40 TeV, the Earth then becomes opaque to neutrinos. So if I ask what is the neutrino flux as a function of the zenith angle when I look through the Earth, I should expect this kind of absorption theoretically. And in IceCube, we looked for the absorption and we found it. So this band that you see here is the absorption that we measured in the Earth, and that is quite consistent with the theoretical calculation that we had made some years earlier, of course, within the uncertainties. And this is very reassuring because this goes up to an energy, as you see here, of 10 to the 6 GeV. So that's a 1000 TeV. It's 100 times larger than the energy at the LHC. And of course, you can invert this argument. If you really believe our calculation of the cross section is correct, then you can infer the absorption in the earth from that and thereby do tomography of the earth. And people have been doing that as well. So beyond 10 to the 8 GeV, the cross section becomes rather uncertain because there can be new phenomena actually within the standard model. You can have the formation of something called a color glass condensate in QCD because of that increasing gluon density I mentioned. You can create objects called sphalerons, which go between different vacua of the electroweak theory and barrier number changing interactions. And that creates a spectacular signature that would increase the cross section. Of course, we don't know this. We have only probed up to energy of 10 to the 7 G. But if we can go higher in energy up to these GZK neutrinos, then we can test these ideas at all experimentally, including new beyond standard model particles like leptoquarks, new dimensions, etc. Okay. Now, very briefly, I realize I'm almost out of time. There is something very interesting you can do here. So many of you are interested in neutrino oscillations. Here we can study neutrino oscillations over astronomical baselines. And what that means is that anything that destroys the coherence of neutrino oscillations over that kind of length scale becomes open to observational scrutiny. So, for example, we can check if Lorentz invariance is violated at the Planck scale, because although the effect is very, very small, it goes maybe as E cube by Planck mass square. It is enough to destroy the coherence of the wave packets and change the flavor ratio that we measure at Earth. And you have recently published some papers in Nature to that effect. So the flavor ratio is the fraction of tau neutrinos, muon neutrinos, and electron neutrinos in the flux we receive. Right now, we can't measure it too well. We are in this blue band here. But you see, with this Gen 2 extension, we'll be able to pin it down to the point where you can, in fact, start doing serious physics at an energy scale which is simply not possible to explore in the laboratory, including non-standard neutrino interactions, sterile neutrinos, at long-range forces, and so forth. So I've been able to give you only a glimpse of the range of physics that IceCube can do, which in fact also includes glaciology, Earth tomography I mentioned, atmospheric science. The muon flux that we measured is correlated with the temperature of the upper atmosphere, which is something that climate scientists are very interested in monitoring continuously. And it is amazing that we can actually measure it, as it were, by detecting muons 2 kilometers underground. I've talked a little bit about this corner of the figure and multi-messenger astronomy, but I hope you have had some idea of the very wide range of physics that can be done if you have a detector like this. And as I said, to detect the flux to higher energies, we need a bigger detector. That is this Gen 2 array, which will be about 10 times bigger, and have a much bigger, 100 times bigger surface array, including radio detectors, which are a lot cheaper. So the total cost of this will not be much higher than that of IceCube. And this upgrade has already been funded. The Gen 2 is in process of being funded. But you can see that we have a timeline for how we will proceed on that. And Gen 2, we hope to start constructing right from next year and deploy in about 3 years. And then we can do real multi-messenger astronomy along with all these satellites and ground-based telescopes. People have already built the pipeline for that. And may I take just 2 more minutes to mention what relevance this might have for Indian physics. So some of you may know that the Cosmic Ray Laboratory, which is run by TIFR at UTI, has now been declared a National Center for Cosmic Rays. And this, we feel, opens up opportunities for participation in these major experiments. So my colleague Mohammad Ramiz at TIFR, he's an associate member of IceCube. In fact, he did his PhD on IceCube a few years ago. And he's also a full member of IceCube Gen 2 from last April. And India will be a full member of Gen 2 when it starts. And proposed contributions include hardware contributions to the cables that are used to insert those detectors in the eyes, to computing. They make excellent scintillators, manufactured them at the UT laboratory, which can also be put to work in the surface array. Radio detectors, we have a lot of expertise in radio detection in India. And of course, we have a large group of excellent phenomenologists whose input will be very valuable. IceCube is really a true collaboration of theorists and experimentalists. Now, I wanted to mention Tarun's talk from a few weeks ago because he showed this and he emphasized that there is a possible synergy of LIGO India with neutrino astronomy. And in fact, IceCube already has a memorandum of understanding with LIGO. And we have actually already made a proposal to coordinate all the possibilities for multi-messenger data using both Indian telescopes and projects abroad in which Indian astronomers are involved. In particular, this LSST project, which will be carried out at the Vera Rubin Observatory and the Cherenkov Telescope Array and so on. So now the map of the world for the Gen 2 collaboration includes India. And as you can see, we now fill in the gap between the Australian and New Zealand and Europe. And that is very pleasing to see because I think this will really offer opportunities to engage with a large community in India who are interested in neutrino physics, in multi-messenger astronomy, and essentially in contributing both with theory and experiment expertise to this international experiment. So to summarize, neutrino astronomy, I think we can say, has come of age because we have detected extraterrestrial neutrinos, which are diffuse, but we have also identified at least 2 sources. We have a few more in the pipeline, as well as detecting the neutrinos created in our Milky Way. Now, the real future lies in multi-messenger astronomy, that is in conjunction with radio, optical, X-ray and gamma ray telescope, as well as gravitational wave observatories, because only then we'll really understand the physical mechanisms that power the engines of these high energy particles in the universe. On the particle physics side, we have also done quite a bit. We have, for example, demonstrated that the calculation of the neutrino cross-section in the standard model is valid up to energies much higher than we can ever probe in the Earth. And we find no deviation from the standard model. That puts strong constraints on beyond standard model processes, as well as on processes within the standard model in the non-perturbative phase. And the last frontier that we are now pushing on is to measure the flavor ratio. We have only very recently got our first tau neutrino candidates. So this has been a long time coming. But once we can measure the flavor ratio precisely, we'll really be sensitive to a very wide range of physics that can disturb neutrino oscillations, or rather their quantum mechanical coherence, over very long baselines. But in order to do all this, we have to think big. So KM3net is going to be also about 7-8 times as big as IceCube, just as Gen 2. And with the 2 detectors, we can cover the whole sky. So I'll end with the words of Marcel Proust, who spent his entire life in a dark room. But he said something which is rather prophetic, that the real voyage of discovery consists not in seeking new lands, but in seeing with new eyes. So thank you very much for your patience, and I'll end with showing you that at the South Pole, we do a very valuable job on behalf of the entire Earth. So here we are holding it up from falling down into the void of space. Thank you very much. I'll stop there.
So thank you very much, Professor Sarkar, for taking us through this fantastic journey of IceCube. And we are waiting for more, path-breaking results. And now I will request my colleagues, Dr. Namit Mahajan and Dr. Ketan Patel, to handle the question-answer session.
Thank you, Subir, for an excellent talk, as always, lucid and clear, and taking us through different corners of physics, what an experiment like IceCube can do, and also towards the end, pointing out different avenues related to present and upcoming experiments, where both theorists and experimentalists could contribute and come together. Now the floor is open for questions. kindly raise your hands, and I will take the questions one by one. So I see Shubhavati already. Shubha, you can go ahead. In the meantime,
Yeah. So, what
I'll
is
check.
the status of the tau neutrino detection? There was some paper, I think, on 2 events detected, but then it was not termed that it's a discovery.
Well, there is a background that we identified for tau neutrinos, which comes from the production of charm. And this is something on which we have had some new data as well. Also, charm production has been measured at LHCb in the forward, at high rapidity, which is where we need the measurements. And we have now satisfied with the simulation we have done of the expected background from that. So you can very soon expect to see a paper. The thing is that I should explain this. In IceCube, we never look for a expected signal just like that. In order to make sure that we don't fool ourselves, anybody who proposes any signal has to first show the science case for it. Then they're allowed to take 10% of the data, which we call the burn sample, and try it out, tune their carts, tune their filters, etc. on it, and optimize it as well as they can. Only then they're allowed to open the box and look at the rest of the data. And that way we ensure that, consciously or unconsciously, human bias is very hard to avoid. And only by blinding the data like this, we can be sure that we avoid that. So when we publish something, every person in that author list is putting their name on it.
Professor Bharadwaj. Professor Bharadwaj.
Thank you, Namit, and thanks, Subir, for a very excellent talk. And we all, I believe, really enjoyed, because we have colleagues from different fields working here, and many of them work in various domains of astronomy, including X-rays, UV, and visible and radio. And certainly, it's a period of multi-messenger astronomy where we talk about combining information from different wavelengths to make a wholesome picture of any process and event. And I would like to inform you, you mentioned about Bibha Chaudhary, that because she worked here for a very significant amount of her life here. So we had started a Vibha Chaudhary Memorial Lecture, and we already had 3 Vibha Chaudhary Memorial Lecture posted. Right. So probably Shubhavati will give you more details when you talk to her in person. But my question was to you is when we talk about multi-messenger astronomy, try to club the information from different groups or different wavelengths, I should say. Is there someone who is actually working on this, or we are still talking about it?
Well, at the moment, we are mainly talking about it, but in fact, quite recently, we actually got together with the people who are operating gamma ray telescopes in Hanle. There's a group from BRC that's doing that. And of course, the people at the Indian Institute of Astrophysics in Bangalore who operate optical telescopes. And Ramesh brought them together, and we are actually going to have he's organizing a workshop in October to bring together all interested parties in India in order to identify what are the possible ways that we can actually club data together. Now, Ramesh actually has experience. He was involved in writing that software for IceCube that sends out astronomical telegrams, the alerts. So we know how to do that. And in fact, we have made a proposal to, as it says here, to indeed integrate data from all these telescopes real time and create a web page on which, just like the one that I showed for IceCube, which is not due to us. This one, let me show. Yeah, this is this website. You can see that people have already been working on how to integrate data from a variety of satellites and ground-based telescopes to have real-time alerts, and also for each of those which receives the alert to feedback what they are finding. So one gets a integrated and comprehensive image in more or less real time. By real time, I mean it could be up to a minute or two after the actual event. So we would hope to do something like this for objects which are in India. And to that end, of course, we are relying on the support and cooperation of all our colleagues doing different kinds of astronomy, because this really requires a very broad range of expertise. Some of us are coming from high energy physics, some from astronomy, some are doing signal processing, some are doing artificial intelligence. It really takes a very broad range of skills to put it all together. So to answer your question, not yet, but we hope there soon will be. And by soon, I mean within a year.
Oh, great. That would be really nice. And this will be a effort which is funded or it is
No,
voluntary?
no, this is not yet funded. So there is a new scheme called Vaibhav that the Indian government has announced, and Ramesh and I put in a proposal under that. So we're
Oh,
waiting to hear. But the truth is that whether it is funded or not, we'll do the work anyway. That's how we work. But it
good.
will obviously make life easier, because if it is
Right.
funded, then we have a coherent platform. We can go to other people with, other data streams and tell them that we have a cogent program, a project that we would like to involve them in. But in any case, we would like to get the job done. Maybe I should say that in case any of the referees are online, but we'll do the work anyway.
No, it's essentially required because all of us work in different domains of wavelength, looking at different objects, but
Yes.
it is always important to combine and see
Yeah.
what is seen at other wavelengths, and that really helps us to understand the complete perspective of
Absolutely.
any object or the phenomenon. Good,
Absolutely.
thank you so much.
Thank
Thank
you.
you, Ramit.
Thank you. Som, please go ahead with your question.
Uh, Thank you, Professor Sarkar, for very informative and lucid. I'll say I'm not from field, but I could understand fully. You showed that for the experiment there is a radio array. So
Yes.
in that radio array, is there some band of the wavelengths, or like that? What the range for that radio array is there?
Yeah. So
Can
this, as I said, is still undergoing. Let me go back to where that slide was. Um, so actually, maybe it's not there. So this is still in the process of being developed. So to date, to answer your question very briefly, nobody has detected a single neutrino in radio so far. Okay. And the range of techniques is very broad. When you look down from the sky from with balloon, let me go back to that slide where I had what is that?
little ahead, I think.
That's a different technique. So for example, the Anita experiment, which actually looks down at the ground from the sky, that in fact, oh yeah, this last slide. Yeah. So these experiments are all operating at different wavelengths because the refraction of radio waves inside the ice, so you put a detector in the ice,
Okay.
that works quite differently from one that is looking at the reflected signal from the ice.
Okay.
Right. So in order to, and right now, the honest truth is that, of course, people have their own favorite options for what would work best. But since nobody has yet detected a single neutrino, I think the race is still wide open, and we'll see who gets there first, right? But large collaborations have already formed to do this, both in Antarctica and the Greenland ice, and also have so-called long duration balloon flights around the South Pole, which look for reflected radio signals. These can also come from cosmic rays. The distinction from neutrinos is somewhat subtle. And actually, the Anita experiment thought it had detected a neutrino signal because of the polarity of the radio signal that was reflected from the ice. But it turns out that that can also be because of multiple layers of refraction within the top layer of the ice. Incidentally, this is something that C.V. Raman did research on, as we find out years later. And it might be that you need to do a bit more glaciology before this technique is established firmly. But at the moment, it is definitely in the R&D stage. In the longer run, there is a proposal for a experiment called GRAND in China, which is mentioned here at the bottom, that hopes to see neutrinos from their conversion to charged leptons in surrounding mountains, so that then a neutrino enters one side of a mountain, out comes the lepton, which then emits a shower in the atmosphere. In fact, the Pierre Auger Observatory also tries to look for such events, because the detectors, those tanks, are a bit off the ground. They were actually raised from the ground to make sure that the cows grazing on the pampa don't get at the solar panels on top.
Yes.
But then it turns out that that also gives us some sensitivity towards so-called earth skimming neutrinos. But again, to date, we have not seen any. We have only placed upper limits on the flux.
Thank you.
Thank
Thank
you.
you, Professor Khan. Thank you, Namit.
Viresh, please go ahead with your question.
Yes, am I audible?
Yes.
Thank you, Professor Sarkar, for a very nice talk. I have a couple of short questions. One is related to this neutrino detection from laser.
Yes.
And you mentioned that it went into flaring state, and then this neutrino was detected. So I
Yes.
was wondering that because there are many blazars which are
Yes.
detected in gamma ray, or let's say TeV, for example, Markarian 421. Has there
Yes.
any been attempts to see that when these blazars go into flaring state, when they are flaring in almost in all wavelengths, whether
Yes.
they have been detected, is there any increase in the neutrino flux? Why
Yes.
only one source? I was curious to know.
Well, so we have, of course, looked at stacked blazars and not found any so far from other objects. But again, as I said earlier, we have a very strict policy of first identifying what is the target we want to look at, what is the analysis you want to do, and only then looking at the data. Otherwise, we might just start going through things and reject, when you report a result, people, of course, get very interested in what you have found, but what they don't hear about is what you did not find, right? So you take my meaning. We must make sure that in doing this, we do not selectively favor just some objects over others. We must be, otherwise we cannot estimate the chance probability of finding them, because all the time you are fighting a huge background of atmospheric neutrinos and muons. So we have to be very sure that whatever think we are seeing from a active galactic nucleus or blazar actually came from there and is not just something that created locally at the same time, which happens to mimic it. So for this reason, we have done stacked searches, and so far the answer is there is historical neutrino emission from a few objects, and some objects have cropped up in a random unbiased survey of the sky, but they have not reached 5 sigma significance. We operate this high energy physics standard that we have to get to 5 standard deviation significance before we will, which is 3 parts in a million of it being a fluctuation, no more than that. Unless we reach that, we are not going to call it, announce it. So I can tell you, there are several objects we have already now seen at 2 to 3 standard deviation significance. And we are now framing the hypothesis, which then will allow someone to do an analysis by then opening the box, looking at the data in a blinded manner to check if that hypothesis actually stands the test. Was
And
that
my
clear?
second question was related to this diffuse neutrino emission, which you
Yes.
said that it is coming from our own Milky Way galaxy.
Yes.
Can't it be a kind of extragalactic nature where you have a GRBs, or let's say a lot of AGNs, and cumulatively they can give rise a kind of a background neutrino? Of course,
Well,
that
actually, what we are saying, what we first detected, the extraterrestrial background, that is very likely from all the sources that you mentioned cumulatively, right? The
yes.
Milky Way emission, I should have emphasized, is much weaker than the extragalactic background. This is very unusual because in all other wavelengths, the Milky Way is brighter than the extragalactic background. But here it is the other way around.
Okay.
Which is why we needed all those clever artificial intelligence methods to isolate the Milky Way signal. The extragalactic sky, to first approximation, is the brightest thing out there. And that is, as you say, the cumulative effect of whatever are the sources. We haven't seen any emission from any gamma ray burst, whether in a stacked search or individual objects. including the very close by one that happened last year, which was the brightest of all time. So it really looks like if nature is creating neutrinos in those things, she's hiding it very well from us.
Okay, okay. Thank you very much.
Thank you.
Subir, there are two questions from one of our students, Supriya Pan.
Sure. Okay.
The first question is, what are the possible reasons for not observing neutrinos from GRBs? What is the expected energy scale?
Well, GRBs have been mentioned as possible sources of the highest energy cosmic rays and thereby neutrinos for a long time. But the truth is that whereas there are any number of theoretical speculations about how GRBs work, there is actually very little hard knowledge about them. There is, of course, many thousands of GRBs have now been logged, and there has been some taxonomy. There are short GRBs and long GRBs and so forth. So there is a bit of botany going on. We still don't know what the actual mechanism is, except that it ultimately must involve gravitational energy, because that's the only thing that can power such objects. But we don't really know whether it is, as in the standard theory of GRBs, it is some central object sending out a beam that then undergoes multiple shocks, and the shocks overtake each other and create plasma instabilities. That is the standard model of GRBs. But then a high energy physicist, Alvaro de Rula, he had a alternative model where the central engine fires out what he called cannonballs of plasma, and he can explain the gamma ray light curve very well from inverse Compton scattering of ambient photons of these plasma cannonballs, right? Actually, right now, we are doing an experiment at CERN on the so-called high rad mat facility, where we take the superproton synchrotron beam, 440 GeV, and use it to try to recreate a gamma ray burst. But that I might talk about in a future talk. I haven't got results yet, except that you have already found something interesting, that the standard model of gamma ray bursts really needs re-examination. So to answer the question, it could be, if there was a standard mechanism that was established for GRBs, then I could tell you, oh, maybe the beam is not pointing at us, maybe the disk is not aligned. But actually, there is no standard theory of gamma ray burst. I mean, people talk about a standard model, but that's simply from the fact that it has been around for decades, so you call it a standard model. There has been no independent test of it. So, in fact, the fact that we don't see neutrinos from gamma ray bursts, it's like the dog that didn't bark in the night. It should tell us something interesting about them. I don't want to speculate any further. Yeah, thanks.
His second question is, how do you plan to deal with the large uncertainty in the cross-section for cosmogenic neutrinos that you plan to detect in IceCube Gen 2?
Well, we plan to, the way you deal with the uncertainty is by actually making the measurement as well as you can, and depending on whether the measurement agrees with the standard model prediction. The standard model prediction is, the per-derivative standard model prediction is pretty good. And certainly the measurement uncertainties are always going to be bigger than that. But the kind of scenarios that I mentioned, scalar glass condensate or sphalerons, they would change the cross-section by orders of magnitude. And that is something that we would certainly detect. And that would be really finding dramatic new physics, not per-derivative new physics, but not per-derivative physics. So I don't think the uncertainty in the predicted cross-section is going to be a problem. It will be more of a problem to actually measure sufficient events, because the cosmogenic flux is very small and likely to be even smaller if the primary cosmic rays are heavy nuclei and not protons. In that case, they don't create the delta 1232 resonance. They photodisintegrate on the infrared background and create neutrons, and those also create neutrinos, but lower energy, so that those are no good to us. It's good to have an eye open for all the theoretical challenges that might come. But currently, I have to say, our priority is to actually just build a detector that will get some kind of a healthy event rate. And then we can come back to these questions.
Thanks, Subir. Durga Prasad, please go ahead with your question.
Yeah. Thank you, Dr. Namit. Thank you, Professor Subir, for a very nice and interesting talk. even I'm not from the field, but I could understand certain things. So actually, I have one question regarding that OT experiment what you have mentioned.
Yes. Yes.
I was able to, I was at UT recent times, and
Yes.
I could see that experiment, actually that
Yes.
array and all, both radio telescope and this one.
Yes.
So I was wondering, I had a short discussion with the people over there, but
Yes.
why OT is selected, they said that that particular location.
Yes.
And particularly when I see that array, so
Yes.
this is actually following a slope pattern. So there,
Yes.
all this array is put it on that small hill slopes, both
Yes.
at that guest house area and also near the radio telescope. So they
Yes.
have followed a particular pattern and a slope.
Yes.
So is it natural or is it purposefully used? That slope was used for any, what is the significance
Well,
of
the
that?
two telescopes are quite different in character. The radio telescope is on a slope which is the same as the latitude, and that way the radio telescope scans in right ascension without having to move at all. Okay, so it only scans in one dimension. It doesn't need to scan in the other one. So that was Govind Swarup's insight. He, in fact, jumped on a jeep, he told me, and went around South India looking for a slope of the right angle. But the slope that you see here for the grapes array, which is
Yeah.
this experiment here, that is simply because a large bowl is convenient to put these detectors on. That slope doesn't have any significance. You could build an array like that on flat land,
Okay.
but they want to be at a certain altitude because the air shower develops in the atmosphere and then dies out. So there is the optimal height that you should be at to catch it close to maximum. Then you get the largest fluxes. So each of these little things that you see here, that is just the rain shield over a detector below it. And this is the old photograph. They have now installed more muon detectors. So this was under the leadership of Sunil Gupta, who was the principal investigator. He may have shown you around. And what he has also done is built up laboratories there, like the one you see here, where they can fabricate hardware, like, world-class scintillators. They manufacture from plastic that is imported from Japan, but they fabricate the scintillator there at a cost which is a small fraction of what it would cost to actually buy it. And this is now being supplied to a variety of universities, the Department of Atomic Energy and other such things. And we will be also needing a lot of scintillators for the Gen 2 surface array. So you see, these things don't happen overnight. They take 30, 40 years to build up and to put in place. And I'm from the same cosmic rays group that ran this experiment right from the 1960s. So there was Professor Ramanamurthy earlier, and then Sunil Gupta, who has recently retired. And Ramesh is now the co-principal investigator of this experiment. The multi-messenger activity I was talking about is not just at Ooty, that, as I said, is in conjunction with telescopes all around India, some of which are at Hanle in Ladakh, and others. There is the tactic telescope I mentioned at Mount Abu. There are telescopes at Gaurivindur and other places around.
Yeah, I have a small follow-up question to this.
Yeah.
So actually, if I have seen this set of detectors, one set is near the radio telescope area, and another set is far away. Where is this?
This
Their
is the
guest house
far
is
one.
there.
There is
Ah.
the radio
So does it
telescope is
have
over
any
the hill.
impact? Because
Sorry?
this distance, does it have an impact? Why it cannot be continuous one? It is only the limitation.
Well, they are just two different units. So the radio telescope, as I said, was set up by Professor Govind Swarup, and it is now run by the National Center for Radio Astronomy, which is also an independent unit of TIFR. This is an experiment that was set up by a different group in TIFR at a nearby slope. They don't have to be next to each other. They are not taking any triggers from each other, right? They are two independent activities. In fact, the original array is not here. That is next to in the botanical gardens in
Right,
Ooty,
that's
about
what I
7
was telling.
kilometers.
One set of array is near radio telescope, another is near botanical gardens.
Yeah, but those are two independent arrays. You have to just make a bigger array to get more fluxes. The one in the botanical gardens, I don't think is operating anymore. They only have laboratories there for fabricating various things.
Okay.
I was there very recently in February. Yeah.
Okay.
In March, in fact. We had a National Science Day celebration, and they do a lot of activity in giving public lectures, and hundreds of school children come.
Right.
So I think it's a rather good thing they're doing.
Okay, sir. Thank you so much.
Thank you.
Subir, we have a question from one of our colleagues, Dr.
Yes.
Neeraj Rastogi. He's asking about the criteria of selecting the location for IceCube detectors, and what is the flux of high energy, flux of high energy neutrinos uniform for whole Earth?
Yes. Well, the answer to that is we have to go to the Antarctica, because only there you can find a chunk of ice big enough kilometer cube in size. We can see here. So the IceCube detector is just this brown patch in here, and you don't find such a large chunk of ice anywhere else in the world. You can, of course, find large chunks of water. That's what they're doing in the Mediterranean, in the Pacific, now in the South China Sea. But doing it in water has advantages and disadvantages. Disadvantages are obvious. The detectors move with the currents. There are things swimming around that can give you false signals. Whereas ice is stable, and this was the choice that was made in this case. The neutrino flux is the same all over the Earth. It doesn't change, because this is coming from very high energy cosmic rays. They are not influenced by the Earth's magnetic field. Okay.
Okay, thank you. Let me just check if somebody else has any other question or. Manash. Manash, please go ahead. Yeah, Manash, go ahead.
Yeah. Professor Sarkar, thank you for your talk. And like one of your slide, you shows the photons and the neutrino distribution around the galactic plane. Okay.
Yes.
So the in one of the panel, you shows the model expectation of the neutrino by the IceCube.
Yes.
Okay.
Yes.
Where I can see around the galactic center, the model expectation is high.
Yes.
Okay, so that's primarily because in the galactic center we have the black hole, which is throwing winds and jets with a lot of high energy photons, and somehow it is correlated to that.
This is independent of what the sources are. This is a template that is derived from the gamma rays. It may well be, as you say, that there is. So the gamma rays are reflecting the interactions of cosmic rays with matter.
Right. Right.
All we are doing is saying that in the same interaction, neutrinos will be created,
exactly.
And therefore the neutrino will follow the gamma ray flux.
Possibly, yes.
What the cosmic rays are coming from, whether it's the black holes or pulsars or whatever, that we can't tell at this stage. But in fact, what you said is a good guess, but that we cannot yet identify, because we can't look through the dust and other obscuring haze and see what actually is creating more cosmic rays there. So now that we have neutrinos, with more events, we'll be able, this is only based on a small handful of events. When we have a real neutrino map of the galaxy, then we'll be able to pick out the sources, because they will just cut through all the surrounding dust and so on. That is the real attraction of neutrino astronomy.
Okay. Yeah. Okay.
Thank you.
My follow-up question is like you said that you use some technique called convolution, CNN convolution techniques, that somehow you're able to remove background and try to locate the neutrinos in more profoundly.
Yes.
So could you please little bit elaborate how you could remove the background?
Well, I'm no expert on that. That is done by smart young people who know about these things. So I could tell you what I know from Wikipedia about convolution neural networks, but I don't really know much about them, except that they are, as the name says, they learn from the database that we have of what different events look like, what their characteristic signature is. And the point is that they can go through the full data. All the detectors have timestamp data in amplitude, position, and direction. So they can go through that entire data set about 30 times faster than we could do earlier with likelihood fitting methods, right? So conceptually, what you are seeing here is that instead of just using a likelihood match, we are using these neural networks which can learn as they go along, and thereby speed up the entire process and essentially process more data. So broadly speaking, that's how it works. In detail, I can't tell you any more than that.
Yeah. Thank you for the information. Yeah, that's helpful. Yeah, Naveen, that's from my side.
Yeah. Okay. Thanks, Manas. If anybody else has any question, please feel free to ask, but do that quickly or raise your hand or type in the chat box.
Yes, actually, I have to. I just realized I went a little bit over time. My fault. I've got another appointment shortly, so I'll have to go
Okay,
soon.
so I don't see any other question or anybody raising their hands. So thanks, Subir, once again for an excellent talk and patiently answering all the questions.
Noted.
And now may I request my colleague Bhala to take over for next set of proceedings. Bhala, over to you.
Thank you, Professor Namit. We have come to an end of an interesting talk and the end of 83rd Amrut Vyakyan. Thanks to Professor Subir Sarkar for sparing time for us and delivering a wonderful talk. You have taken us to the South Pole and showed us how science is done irrespective of the harsh environment. It is a classic talk to teach us about neutrino astronomy, looking at the universe from beneath the ice sheets. So we can look at the universe even from very harsh places. This Vyakyan is one another great value addition to our Vyakyan series. This talk will be available for anyone to see anytime in PRL YouTube page. Many thanks to our audience and thank you for those interesting questions. Thank you, Professor Shubhapati, Professor Namit Mahajan, and Dr. Ketan Patel for helping us to successfully organize this 83rd PRL Amrut Vyakyan. Thank you to our director, Dean, Professor Nandita, Professor Lokesh Shahu, Dr. Bushir, many other Vyakyan committee members, and all PRL members, as this is the chain that keeps the PRL Vyakyan pulsing forward. Before we conclude, on behalf of the members of PRL, I would like to once again thank Professor Subir. Stay tuned for the next Vyakyan. Thank you.